Hello physics students. In this video I'm going to be explaining what variable resistors, switches, ammeters, and voltmeters are, and also how to connect them properly into a circuit. So this video is going to be a little different than the other circuit videos in that there won't be any calculations. Everything will be conceptual with drawings. So the first thing, the variable resistor. What is it? Well, as you might imagine, it's a resistor you could vary. So here's the symbol for the variable resistor, and you don't have to remember this. As I've said throughout the topic, the symbol for a variable resistor is in the reference table here. Wait for the focus. Right here you see that symbol. So what is it? How does it work? Well, if you see, you got this long resistor here and this contact point which you could slide around. Now if you slide this over to this side, the current gets deposited out of the battery here, and it doesn't have much resistor to go through, so the resistance is small. In fact, if you move the slider all the way here, you could, in theory, get to zero resistance. As you slide this contact point further to the left, the current gets deposited and it has to go through more resistors, so we can have zero resistance more and more to some maximum value. Now we use this in I used it in Ohm's law demonstrations when we were talking about Ohm's law. So what I'm going to do is sort of use a little, time travel a little bit, just a little bit, so you can see that. So I'll briefly send you so you could look at that variable resistor and see what it actually looks like. So brace yourself. Here we go. We see this is very little resistance, and I'm going to add more resistance, and you see the bulb brightness goes down. Some more resistance, we would have seen less current if I had the ammeter there. We see that through the bulb brightness. Okay, so that was the variable resistor. The next thing we're going to do is talk about a switch. So what does a switch do? Well, it turns current on and off. So first thing, this is a schematic of what a switch looks like. So what you have is you have some wire that's connected here and a wire connected here. So the electricity wants to pass through this switch, but there's an air gap here, so the electricity can't flow. So this is now, right now, in the off position, which we say is open. When you close the switch, it's in the on position. This metal, well, it's cardboard, but if it were metal, it would come down and contact this piece of metal, this post over here. Now the electricity can flow through the switch and out the other end. So off, open, closed, on. Okay? So now I'm going to show you actual switch, what it looks like in an experiment I did with another class. So again, time machine. Brace yourself for a little journey. The first thing you're going to see is me installing this switch onto what we call a proto board, getting it ready for the experiment. So here we go. So what I want first is the switch. So I will put that in right here. And that's going to control the electricity coming from this positive terminal. And right now this switch is open, so it cannot get to this row. But when I close it, of course, it will. So the first thing I want is the 3000. All right, so that was me installing it into the circuit. The next little clip, a few seconds, I'm going to show when I close the switch. It won't be that clear in the experiment because it's not a good angle, but you'll see me turn the circuit on when I close the switch down. So here we go. In a sense, by watching this ammeter. So watch what happens, okay? So I go like this. And now, why is it? All right, so in one more little clip, I'm going to open the switch back up and you'll see me turning the circuit off. So brace yourself. It'll go down to a value we could read again. So here we go. Ready, set, go. Okay, there it is off the scale. All right, so that was me opening the switch up again. Now what I have here is I want to show you a switch from a household circuit. So let me come close to the camera. Hopefully this shows up. I don't know how well this will show up on the camera, but you might imagine this is like a light switch in a wall. It should look familiar, at least this part, where you turn it on and turn it off. So the same kind of mechanism works with this. First of all, we have wire contacts, some screws here. We wrap the wire around two wires, and those represent the current coming in and out. And then we could interrupt and connect that circuit by turning on and off. So I drilled this, the thing holding this together so I could take this metal off right here. Let me just drop that, and then I'm going to take this plastic off. And for the before I put it down, you could see that when I switch like this, it rocks this plastic back and forth. There's a little bit that gets attached to a spring to give the switch a nice click when you turn it on and off. But the crucial part is this metal here. Let's see how I could. So I don't know if you see it, but this screw post right here connects to this part of the metal, and this one down here connects to this part with this contact right here. When that plastic swivels down, what happens is it depresses this right here. Let's see, right there. And it presses it in and makes that separation between the contacts. So you see the spring fell out. But so this would be open right now. The switch would be off. And then I click the plastic the other way, and it allows this spring to spring forward and make a contact to that other piece. So now it's closed or on, and then you switch, it's open or off. On, off. So that's a household switch. Let me just put this down here. All right, so how do we sketch that in a diagram? Well, once again, this way to draw it is in the reference. I won't go to the camera again, but if you ever confused, go back here. You'll see how to draw it. But essentially what you have is you have in here like a piece of the circuit going off like this, and now you see there's a gap here. This I label switch A, and this switch B. Now what do these switches do? Switch A controls the total current. Notice no electricity can flow to either of the resistors because there's a gap here. By the way, it doesn't matter if I put the switch before or after the battery. Remember, a circuit has to be a complete loop. Make a break anywhere in that circuit, the electricity will not flow. I could shut it off by creating a gap, on the negative side of the battery also, fine. So I open it, and then when I switch this down, it makes a contact. Now electricity can flow past switch A, so it controls the I total, making it on or off. Switch B, though, cannot control resistor 2 current, because once this closes, the current can go through resistor 2 even if switch 1 is open. Switch B is open. So switch B will only control I1 on or off, okay? But if switch A is open, it doesn't matter what you do with switch B because no current can get to either resistor. Switch A and B must both be closed for I1 to be not zero. So let me give you a moment to copy these notes down if you need a moment to catch up. Okay, so let's move on. Ammeters and voltmeters. So first thing, what I have here is called a multimeter. And let me get closer here. Why is it called a multimeter? Because it can measure multiple things. Turn it on, and I could turn this dial in a whole bunch of different places. So if I turn it to where it says V, first of all, there's two kinds of V that I can measure. This one is battery voltage or direct current, like I talked about in the first lesson. This with the squiggly line measures alternating current, like the voltage in a wall outlet. So if I turn it like this, then I connect these probe wires. I'm going to plug in one into COM. These meters work where one of the wires must always go into COM, no matter what you're measuring. And the other one I'm going to plug in here where it says volts, ohms, and hertz. So if I go like this and turn the dial here, this multimeter is now a voltmeter. If I leave this here, also where it has ohms, and I turn it to over here, it measures resistance. it's no longer a voltmeter, it's an ohm meter. And later I'll configure it for amps or to make an ammeter in a minute. Actually, I'm doing amps first, so I got it backwards. So then I turn like this and I can measure amps. It's now an ammeter so long as I move this to either one of these holes. Maybe I'll put it here, and now it measures current. It's an ammeter. So this is one brand of meter. You see it's blue. What I'm going to do is use our time machine again. Hopefully you're not getting sick of all this time traveling, but I'm going to, send you back in time so you could see me setting up a circuit and inserting an ammeter into it to measure the current in that circuit. So brace yourself. It's reading 0, obviously, because the current's just sort of flowing past the meter. In order to measure the current, what I have to do is first open up the circuit and then connect the wires, complete the connection with the ammeter. So the important thing about the ammeter is that it must go in series with the circuit. See how this is in series? It's all one chain. You put an ammeter in parallel, not only is it not the way it's supposed to work, and it won't work, but you could create damage, and I'll explain why later in this video. It must be within the loop. I could have put the ammeter here, before the bulb, after the bulb, it doesn't matter, because I in a series circuit is the same everywhere. So we see 0.39 amps being produced. So it's, in a sense, it's like a toll booth for the electrons. And, you know, toll booths, you have to drive through them to be charged a toll. So it's this here, the electrons driving through, and then the toll registers here. But what we want to do is we want to make an ammeter such that it doesn't restrict the current. Because if there was a high resistance here, without it, the bulb would be nice and bright. But if this had like 1,000 ohms, and then I go like this, suddenly the REQ of this circuit would increase, more resistance, less current, and the bulb would be dimmer. I would be changing the circuit if this had a high resistance. So they're designed to have as low a resistance as possible. Hopefully you want 0, but of course nothing is 0 resistance, so you try and get it as low as possible. So that's an ammeter hooked correctly into a circuit. All right, so ammeter, it measures current, and as I said in the video, it must have a low resistance. Ideally, it would have a 0 resistance, but nothing has 0 resistance. But if a manufacturer could, they would make the resistance of an ammeter 0. But they try and make it as low as possible. And the reason why is that it must be in series with the circuit because, as I mentioned in the video, or in the thing you just watched, an ammeter acts like a high-speed toll booth on a highway, registering cars or electrons passing through it. So right here, this is connected correctly because any electrons that flow through these resistors, any current, must pass through the ammeter also. And by the way, it doesn't matter where you put the ammeter. It can be here, 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 anywhere in the circuit within it, and it's now an ammeter. So this is, yes, the current will be total volts over total resistance. So what I would do in real life, as you saw in the video, is I would have these wires within the circuit like this to measure amps. But the difficult thing with an ammeter is that because the resistance is low, there's a danger where you could actually cause damage. This is showing an improper setup that doesn't actually cause damage to the meter, but nonetheless causes the circuit to become distorted and give you the wrong measurement. So what happens? Why is this not correct? First of all, notice this ammeter is in parallel with this resistor. And so what happens is, let's say this is 1,000 ohms. This is very nearly 0 ohms. And so what happens is the current bypasses the resistor 1 and goes through the ammeter instead. So the current in resistor 1 becomes 0. And the current in the circuit is not what we would expect from a series circuit. The only resistance for the battery is the resistance of resistor 2. So the current changes and increases because you took these probe wires and touched them to either side of the resistor like this and ended up bypassing that resistor. So I put no, meaning that's not correct. Now, this setup, big no with an exclamation point. This doesn't damage anything. This would damage either the ammeter or the battery. Okay, why? Well, if I take this ammeter of almost no resistance and I touch the wires like this, there's a circuit here, a loop, with almost no resistance in it. And when you do I equals V over R, with R in the bottom being close to 0, the current becomes very large or nearly infinite. And what can happen is you could burn out the meter or burn out the battery. It's called in electricity a short circuit. And that's always bad in electricity, creating a short circuit, because current spikes and you could have damage or even an electrical fire. If you have a short circuit in a house, the whole house could burn down. So short circuits, bad, okay? You don't want that to happen. So here are some examples. Let me create a pause to allow you to copy these examples down. All right, let's move on to one more example that's more complicated. What I did is I put 3 ammeters into a circuit here. And it's a simple parallel circuit. We've got a voltage source, 2 resistors, 3 ammeters in these locations. This, well, maybe we should add the word yes, so you know that this is all set up correctly. But you also need to know what each ammeter actually measures. For example, if you look here, this is a high-speed toll booth. No resistance, the cars can pass right through. What it's going to measure is all the current coming out of the battery before it splits to the 2 resistors. So ammeter A, you have to be able to look at that picture and realize that it measures the total current in the circuit. Once again, you could put it over here if you want. You don't have to put this in your notes, but I just want you to know that you could put it after, because the current joins again and goes through, so that's a correct location for measuring the total current as well. But ammeter B, notice that any current that's destined to go to resistor 2 never goes through this toll booth. It goes along this road, through this toll booth, then resistor 2. So ammeter C registers the current in resistor 2, and ammeter B measures it only in resistor 1. So again, you have to know. Again, these can go resistor first, then ammeter. That would also work perfectly fine. All right, so the next thing we're going to move on to is the voltmeter. I already mentioned that, I just have to turn this. Now it's a voltmeter to the right spot and move this wire here. Voltmeter now. Okay, so what I'm going to do is first send you back to an experiment where I was hooking up a voltmeter correctly into a circuit. So here we go. Ready? Figure in a different way to do a different thing. This is an ammeter. This is a voltmeter now. So again, remember, voltage is always between 2 points. So now when I take these voltmeter probes, if I want the voltage of the light bulb, what I need to do is measure, not like this, but from one side of the bulb to the other. And that means touching this here and the other wire on the other side of the bulb, and you see that you get a reading, looks like about 3.6 volts of the light bulb. So notice now that since it's from one side of the bulb to the other, is actually connected in parallel to the light bulb. Right? So it's not in series. It's not within the original chain. It's like off to the side in parallel with the bulb. And that's how you use the voltmeter. Okay? If I wanted the voltage of the batteries, I could go here in parallel to the batteries. And I get the same thing, approximately 3.7 volts. So since it's in parallel, What that means is that the resistance here had to be low because it was in series. Here, since it's in parallel, we don't want any of the current to skip the light bulb and go through the voltmeter instead. That would change the circuit. We want it all to still go through the bulb and none to go this way, which means that the voltmeter now has to be built in such a way that it has a very high resistance. Ideally, you would want an infinite resistance. No such thing, though. So a typical voltmeter like this might be like 10 million ohms. So a little tiny bit of the current goes out and bypasses the bulb, but you try and minimize it as much as possible. All right, so voltmeter, it measures the voltage in a circuit, obviously. It has a very high resistance. It's designed to be in the millions of ohms. And that's because it must be in parallel with whatever you want to measure the voltage of. The resistance is so high, in fact, that if you set a voltmeter up properly, you could stick these straight into an electrical socket. So I did that in school, in a classroom. So what I'm going to do is send you to the time I stuck a voltmeter probe wires directly into an electrical outlet so you could see what all the prongs are and how to measure the voltage correctly. So, ready? Here we go. It means that it's perfectly safe to stick, well, I shouldn't say perfectly, because you still need to know what you're doing, but it's safe to stick these prongs into the outlet and measure the voltage. First, though, I have to configure the voltmeter properly. I turn it to 200 V with a squiggly line. That means it's going to be measuring alternating current, oscillating current like the outlets in the wall, and it can measure anything up to 200 volts. So then what I'm going to do is stick in here. Now, first I want to explain what all three of these connectors are. The smaller connector, the smaller prong is what we call, electricians call the hot terminal, the hot wire. And that means it's the one that has the voltage going to it, the oscillating voltage. This is called neutral and this is called ground. Both of these are literally connected to the ground, planet Earth. If your house is wired properly, you can go outside where the service comes in and look for a spike, a copper spike that's driven into the ground to ground your house and ground this prong and this, by the way. So these are 0 volts at all times connected to planet Earth. So in theory, it's possible to stick a paper clip in both of these, holding it with my finger, this one right here, that one, and that one. Of course, you don't want to do that because electricians do make mistakes too, and sometimes they wire this incorrectly. And so you don't want to find out your electrician that wired your house made a mistake by getting electrocuted. So it's never a good idea to test electricity with your body parts, right? So you want to use something like this, a voltmeter. So now that I have it configured correctly, I'm going to stick the 2 prongs into these 2 outlets to measure the voltage difference between the two, the hot and the neutral. So there I go. I've got them in there, as you can see, and it's somewhere around 120, which is the standard in the United States for the voltage of an outlet. In Europe, of course, you may have heard it's 220. They have a higher operating voltage. So I'll take these out now. So that's the voltage between those 2 prongs. But I could also measure the voltage between ground and that hot. Maybe I'll go like this from this side to maintain a good connection. And the hot, and I should get 120 also. Oops. I got to find the right connection in there because the prong size is not correct, but where is it? There it is. So 120 between the ground and the hot. Now, the voltage between the neutral and the ground is 0 because they're both connected to the earth, so there's no voltage difference. So interesting how you can use a voltmeter to even measure the voltage of an outlet at home. All right, I guess I should say, now that we're back, don't try that at home, right? Because if you don't really know what you're doing, you might do something wrong and create a problem. You know, you shouldn't be sticking wires randomly into a socket. So make sure, if you ever want to measure voltage, make sure you read the manuals of an electrical socket and maybe watch some more YouTube videos about how to do it properly so you don't get yourself hurt if you're trying to measure the voltage. All right, so voltmeter there, I already explained. So this is how we would connect the voltmeter in a circuit So one possibility, let me just put this like this, is I take these probe wires and I put them on either side of the voltage source. Red is to the positive, and maybe this is like a 9-volt battery, and then it would read 9 volts on this screen. By the way, if I switch these, it would just read negative 9 volts because the voltage would be backwards according to the polarity of the meter. So that's good. Notice that the voltmeter is in parallel with the battery, perfectly fine, measures the voltage of the battery, okay? And then if I wanted to measure the voltage of resistor 2, what I would do is, as you could see, these are like the probe wires. I would touch them to either side of the resistor. Remember I said this voltage is always 2 sides, 2 points, so you can't go like this. I said that in the video. You have to put one wire on either side of the resistor. This would correctly measure the voltage in resistor 1. If I wanted to measure the voltage in resistor 2, I'd go like this with the wires. So let me write a little bit more about what all those various voltmeters measure. But before I move on, let me create a pause to give you a chance to catch up if you need it. All right, so, VA measures the total voltage of the battery. VB measures voltage of resistor 1. Okay. All right, so that's what those do. Now I want to show you a way you can hook up a voltmeter and hook it up incorrectly. So this is our circuit. So this is just a regular no with no exclamation point. The reason why there's no exclamation point is because you're not going to damage anything with a voltmeter. I can't think of any way you can hook it into a circuit and cause damage. Because what it is it's a very high, nearly infinite resistance. So if I do this, all that I'm doing is essentially stopping the current. This turns I to 0. So without the voltmeter, maybe there's 2 amps in the circuit. We hook it in that way and suddenly it stops all the current. So that's the worst thing that can happen, is you block the current with a voltmeter. So that's why it's not no with this causes maybe a fire. This just makes your circuit turn I into 0. Okay, so let me create a pause to give you a chance to copy this down. All right, so that's it for today. We learned about variable resistors, switches, how they operate, how you can control different parts of the circuit with switches, and how you can measure voltage in a circuit, how you can measure current in a circuit with a multimeter configured to either be an ammeter or a voltmeter, and then hooking them correctly into the circuit properly. So at the end of this video, look back at all the diagrams and make sure you can understand why each diagram is either correct or incorrect for voltmeters and ammeters, because that's also part of the curriculum, that you know how to put these in to measure various things and how to diagram them into a circuit to achieve a certain function. All right, so I hope you enjoyed the video. I hope you enjoyed the demonstrations, the little light switch that I showed you from a household circuit. I'll see you in the next physics video.